Well, hello again. We are now going to get into the heart of the matter here and begin by discussing the engineering design process. So it turns out, just like scientists have the scientific method to produce knowledge, so do engineers have a specific process that they follow in order to create products. So this process looks like this, okay? And you'll see it in different forms, different configurations that are slightly different, depending on where you look, but they all amount to the same thing. The engineering design process begins first and foremost with the identification of a need, typically a need that will serve a market and that people will be willing to pay something for. Okay. Following that, there's a translation from that need to product specifications. Okay. From there, engineers will go on to develop concepts, then on to develop detailed designs after they've analyzed various concepts. And then at some point, that detailed design, after being prototyped, will enter initial stages of production, then mass production, finally distribution, leading ultimately to the end of life cycle for the product. Let's talk about these in turn, but not before first making the important point of the iterative nature of these steps. This is not a serial process. I mean, broadly speaking, it is. But at every turn, there may always be the need, to go back to an earlier stage in the process. So that's what those arrows there symbolize. And then you can think of a large arrow encircling the entire process, basically to the effect that even after a product is in production and distribution, the new one is waiting in the wings, to replace it. So engineering design is very much a living process and an iterative process by nature. And this is something that I'm certain will not be lost with you as we get deeper and deeper into the course. Let's say just a few quick words about each one of these steps. Market need identification. Okay, so every engineering endeavor begins with a recognized need. Okay. Now that can come from multiple sources, but consider, for example, the mosquito, our worst enemy in all of nature. Okay, there is a recognized need, for example, for getting rid of mosquitoes, or at least allaying the damage that they cause. Okay. Besides a very plain, obvious, common recognized need, such as the eradication of mosquito populations, there may be some needs that arise from technological or social trends. Okay, so we see that in many contexts. For example, populations becoming older in more advanced societies, give rise, to entire new needs in the context of engineering. Even communications technologies, give rise, to greater needs or unanticipated needs, for how to deal, with increased communication that occurs, between people, the increased expectation for example, delivery of educational content, would be an example. Okay, for companies that are more in a role of product development and product maintenance, if you will, a lot of the needs will actually come directly from the customer base. Okay, and some tools of the trade for that, will be market surveys, that the companies will sponsor, in order to find out, what customers want in the next generation of a product, and then also focus groups. Those are two well-known techniques in the marketing arena. Okay, let's look now at product specifications. So we've identified a need. We want to translate that need into specifications. Okay, so those specifications will typically take the form of what's known in the so-called Kano model as the musts, the shoulds, and the coulds. So what must be present in the specification, what should be there, and what could be there. Okay, so if we speak of different levels of satisfying the customer needs or customer requirements. Okay, so if you think in terms of performance requirements, those tend to be, we could speak of a scale to the extent to which a product will perform. So if you think in terms of size or weight, the speed, the characteristics of the user interface, those tend to be performance requirements. And as engineers, we want to make sure that those performance requirements are translated into quantitative values to the extent possible. Okay, so we don't just want a fuel efficient vehicle. We want a particular level of fuel efficiency. We don't just want something to go pretty fast, but we want to be able to accelerate to 60 miles an hour, says there in under 8 seconds. And we always want our products to be affordable. This performance requirement never goes away in engineering. No matter what you're doing, cost is ever present in there. Now, beyond performance requirements, we also have constraints. Constraints tend to be more categorical. It's a yes or a no. It's a must have this, may not have that. So if you think, for example, of an instrument that needs to go or that is monitored, say for instance, a patient vital that's going inside an MRI machine. Well, a constraint would be you cannot have any ferrous metal in there because that would rip through the customer on its way to the large magnet that is an MRI. So the need to use plastic components instead of ferrous components would be an example of a constraint. Okay, from market needs to performance requirements and constraints, we then start conceptualizing. Well, how could we do this? That is the fun part. Okay, this is when we start, thinking, how are we going to satisfy that need? Now, concept development begins above all with what some folks will call filling up your brain. Okay, the first thing to do is to research. Become as familiar as possible with everything that's been done. You're going to be standing in the shoulders of giants, or if you're going to do something new, you need to understand, what's been there before. So research is an important and essential component. There are some techniques, mentioned them briefly here: functional analysis, decomposition. Okay, so we look at a need and we break it down into its essential components. So best understood with an example, consider, for example, a lock. Lock as in the lock for a locker or a door or a barn door or something of the sort. So functions of that lock, would be, well, of course, you do need a locking mechanism of some kind. Okay, it needs to be tamper resistant. So that's a function that it needs to be able to maintain. Okay, single user in the sense that you don't want your lock to have the same combination. That somebody could just buy another one and go open yours. It needs to be resettable, potentially. If it's been compromised for some reason, you'd like to set it to a new combination. May need a backdoor. May need some means of getting to it if you've lost the combination. Okay, so that could be debatable. Maybe you want that there, maybe not. Weather resistance is another function that it must fulfill. Okay, so it's important to systematically look at, decompose, the different functions of the concept that you're pursuing. Okay, brainstorming is a very typical technique for coming up with different ideas, and there are well-known established routines and techniques for doing that. Preliminary configuration analysis. Okay, so this is where you will start to put together a potential configuration. Well, it could look like this, it could look like that. Seldom are you blessed with a situation where only one configuration is the obvious and the correct one. And of course, this makes engineering challenging and interesting at once, in the sense that there's typically more than one way to skin the proverbial cat. As you analyze these preliminary configurations, okay, you may want to avail yourself of some quick proverbial back of the envelope checks. Okay, so that's what I mean there by preliminary analysis. At some point, you're going to have these concepts, and you're going to need to make a decision. You're going to need to move forward on one. You want to try to eliminate bias, personal bias, to the extent possible from that process. As engineers, one of our big failings is to fall in love with our design. We call it the ugly baby syndrome. Our baby may be ugly, our design may be ugly. We just don't want to hear about it. We don't want anybody to tell us that. Designs become intensely personal, so it's important, in order to arrive at the best design, to depersonalize it. These decision matrices and then the eventual down select are an access to that. Once we get to the detailed design, this is where we're looking for detailed geometries. We're doing the harder analyses, if you will, in there. We start prototyping. We start creating the eventual embodiment of our inspirations. Now, and undoubtedly, this is where we're going to find out what works and what doesn't. Particularly as we prototype, as we make proof of concept models, etc. Okay. Now, detailed design will involve the generation of geometries, as you see there on the bottom right. It will also involve the generation of engineering drawings, or what's known more modernly as technical data packages. Okay. We'll do that in consideration of standards. We'll revisit that concept here in a little bit, and it'll be important throughout the rest of the course. We certainly will lean on the analysis capabilities of the software that we use to generate those geometries. That's an example of something known as an FEM, finite element model analysis. Okay, we will avail ourselves of prototypes. We've all heard of rapid prototyping. There are many other prototypes that do not require the use of those machines, but we have a nice mix in there available to us. We'll also pay attention to regulatory environments, particularly if we are in industries such as aerospace, such as medical. Okay, so FDA, the Federal Drug Administration would be an example of that for any and all things medical. Okay. Now, finally, the product will go into production and then eventually distribution. Okay, so those are topics that relate more to manufacturing, in fact, to marketing, sales, and then the product again will engage in what's known as a life cycle. There will be revisions to it. Again, remember, design is a living endeavor. Any design is a living product. You don't come to an end with it. In fact, it's often said, that as engineers, we don't ever finish anything. We just walk away from it. Interesting thought. Okay. All right, so there it is, the engineering design process in all its glory, with the attendant feedback loops.